now I'm going to do some practice problem for the non-inverting configuration for the op-amp. So the first question asks for please use superposition principle to find out what is this output voltage here, given that we have these two inputs. So there's different ways to go about doing this. We could use the formula that we have solved earlier of this kind of circuit for the input and the output and the gain, but I rather not do it that way. I rather just try to solve the circuit directly, then we will maybe we will understand better. So to do that, we have to use superposition principle. What superposition principle says is you consider the inputs alone. So first you consider V1 alone, and while you connect V2 to the ground, then you find out what is Vout. Then after that you do the opposite, so then you put the ground on V1 and you apply V2 and you find out what is Vout. And then you add the two Vout together and that will be the final answer. So first step is to consider V1 alone. So this is the first half of the superposition. So so let me just copy the circuit, put it down here, and I make it a little bit smaller so we have more space. So the first step is to consider the V1 alone. So what we do is we connect V2 to ground and we only apply V1. I'm going to make this vertical so it can be a better shape. So I'm just going to rotate this 3 kilo ohms like this. Okay, I'm going to define a couple things right now. First of all, we know that in the ideal op-amp, no current enters the input terminals of the op-amp. So in that case, we know that this current here is equal to this current here. So I'm going to define this current path as called this I1. In the same way, we know that because no current enters the op-amp in the ideal op-amp, so then we know this current is equal to this current. I will then define this current path as call it I2. And then thirdly, we know that in the ideal op-amp there is a virtual short circuit assumption. So we know that the V minus is equal to V plus, and we call this voltage, we call it Vx. Again, in the ideal op-amp. So now we can use this principle. So I'm going to first go on the virtual short circuit principle, which I had just said was in the ideal op-amp, V plus is equal to V minus is equal to Vx. Okay, so the question is, how can we actually solve what is Vx? Well, so right away, immediately, I can notice that, well, you can see that V1 is a voltage source, and then there's two resistors in series to get to ground, and then Vx is tapping the middle point of this between these two resistors. So right away I can see that they have this, I guess, resistor divider path. So just using the resistor divider, and we'll see if this works. So we'll use the resistor divider network, and as you know, it is the input of the resistor divider multiplied by so what sits in the denominator is the summation of the two, so the 2 kilo ohms and the 3 kilo ohms resistor, and what sits in the numerator is the bottom of the voltage divider, so we call that the 3 kilo ohms. So again, it's just this This is the bottom resistor, this is the top, and then the numerator is the summation of the two. So then with the resistor divider formula, you can see that Vx is equal to V1 times, so the kilo ohms cancels. So what you're left with is 3 divided by 5. So Vx is equal to, well, so 1/5 is 0.2, so times 3 is 0.6. 0.6 V1. I'm going to underline this and save this equation. Okay, now before I move on, actually I forgot to mention that because we consider this a V1 alone and we apply the V2 as ground, so we're going to call this V out 1, just to be a little bit more clear. Okay, so in that case, so we use the bottom path just now of this to find the Vx. I think we use the top path this time. So now let's consider this current path, this I1 path here. So we know that this I1 through the 1 kilo ohm resistor is the same current as the I1 that goes through the 9 kilo ohm resistor. So what I'm going to write is I1 and I1. So you know that I1 is equal to this voltage minus this voltage divided by this resistor. So we can say it's 0 minus Vx divided by 1 kilo ohms. And in the same way, the current through here, I1, is equal to this voltage minus this voltage divided by this resistor. So then it's also equal to Vx minus V out 1 divided by 9 kilo ohms. Okay, and now I'm going to cross multiply across this equal sign. So we have the 1 kilo ohms here multiplied Vx minus V out 1 is equal to 9 kilo ohms multiplied 0 minus Vx here. And that is the same thing. You see the kilo ohms, it cancel. So Vx minus V out 1 is equal to negative 9 Vx. And then I move the Vx to here and then cancel the minus sign. So, well, actually, let's just first write V out 1 is equal to negative 10 Vx. So then V out 1 is equal to 10 Vx. And just note that we solved Vx before, so we can plug this Vx go into here. Now you know that V out 1 is equal to 6 V1. So I'm going to save this equation for later. Let's call this superposition 1. Okay, now the second half of the superposition is to consider V2 alone this time. Okay, so I'm going to bring back the circuit. So I just copy the circuit from the problem and make it a little bit smaller. Yeah. Okay, consider V2 alone. So what is that? V2 is now applied to the ground signal, and V1 becomes the new ground. Yeah, so let me just rewrite this circuit to be a little bit more nicely oriented. So I'm going to make the flip to orientation here, so it will be the same circuit, just more clear. So So here's the here's the 3 kilo ohm resistors here, and goes from V2, while the 2 kilo ohms resistor goes to ground. Yeah, so I'm going to solve the same circuit the same way. So just like before, we remember that in the ideal op-amp case, there is a virtual short circuit. So these two nodes here are both the same voltage, called that Vx. And then also we know that no current enters the input of the terminal of the op-amp. So we define this current path, call this one I1, and likewise this current path, we call this one I2. Yeah. Okay. Well, so let's start with the virtual short circuit assumption that we did last time. Same thing as is part of the V plus is equal to V minus, which is equal to Vx in the ideal op-amp, the virtual short circuit. Yeah, so again, the bottom, this is a very similar circuit again. Oh, actually, before I move on, let me just call this one Vout 2, so we don't get confused. We're doing superposition 2 this time. Anyways, so same thing as before, you can see that V2, and then there's a current divider of 2 resistors in series. So Vx is equal to V2 multiplied by the lower resistor is 2 kilo ohms, and then the summation, the denominator is the summation of the two resistors. Yeah, so yeah, in this case, again, kilo ohms cancels, so what you're left with is Vx times, Vx is equal to, well, so that's 2 divided by 5, so that's 0.4, so Vx is equal to 0.4 V2. Yeah, okay, I'm just going to save this equation for now. Let's proceed with the exact same thing we did for the first superposition. For this time for the upper current path, let's do this for the I1. So you know that I1, well, so I'm just going to write I1. So now we know I1 is defined by this voltage minus this voltage divided by this resistor. So I1 is equal to 0 minus Vx divided by 1 kilo ohms. In the same way, this I1 is equal to this voltage minus this voltage divided by that resistor. So it is Vx minus V out 2 divided by 9 kilo ohms. Again, we do cross multiply. So we have, well, first of all, just see that with the kilo ohms it cancels. So we have Vx minus V out 2 is equal to negative 9 Vx. Okay, so I think same thing. So negative V out 2 is equal to negative 10 Vx minus Vx on both sides. And then the V out 2 is equal to 10 Vx, or it's the same as before. And then you can plug this Vx that we just solved into here. And what we are left with is V out 2 is equal to 4 V2. Okay, so the second superposition is done. I will save this equation as superposition 2. Now step 3 is to do the combined, superposition Superposition is meaning combine superposition 1 with superposition 2. So V out is equal to, now you see why I called it V out 1 for the first superposition, and then I called it V out 2 for the second superposition, because V out now is equal to V out 1 plus V out 2. Now we say V out is equal to V out 1 is 6V1, and V out 2 is 4V2. And then here is the final answer. Now in this problem, it is asking for us to solve a very similar circuit, but what was once in the previous circuit that we solved, what was once this ground, now it becomes additional input called V3. So how we can go about solving this is the exact same strategy. What we could do is we could solve the superposition 1, then superposition 2, and then superposition 3. But since we have, in the previous problem, we already did the first two superpositions, we can just skip straight to the third superposition now. What that means, we just inherit from the previous problem. We know that V out is equal to 6V1 plus 4V2. But now with the additional input of this new V3, we have like a coefficient term multiplied by V3. So we know that this problem will need to, the answer will need to occupy some sort of resemblance to this format right here. Okay, so let's just skip to the third superposition, which is to apply V3 alone and then put the ground on V1 and V2. So let me just copy this circuit here, and then I will put here. And also what I need to do is, so again, you apply the signal on the V3, and then you put the ground on V1 and V2. This is like third superposition 3. Which is considering V3 alone. Yeah, so like in any ideal op-amp case, they have something called virtual short circuit approximation, which says that in the ideal op-amp, there is a virtual short circuit here, such that V minus is the same voltage as V plus. We call that Vx. So in that case, we can solve for Vx. Now, very similar thing going on is that, well, because this bottom part is connected to these two grounds at this bottom part, we will try to hold off on analyzing that for the moment. Let's just look at the top path for now. So yeah, so we know that another case of the ideal op-amp is no current should enter the terminals of the op-amp. So as a result, we can know that this current equal to this current. So we define this current path, we call this I1. Then I1. Okay, so we know that I1 is defined by this voltage minus this voltage divided by that resistance. So it's V3 minus Vx divided by 1 kilo ohms. Same thing as this voltage minus this voltage divided by that resistance. So it is Vx minus V out divided by 9 kilo ohms. So now let's do this consideration. First of all, the kilo ohms cancel. Upon doing cross multiply, you will see that 9 times V3 minus Vx is equal to Vx minus V out. Now, actually, I forgot to mention again, we're considering the superposition case of V3 alone. So we call this V out is V3, V out 3. So I'm going to call it V out 3, so we don't get confused later. Okay, so I will now distribute this 9V3 minus 9Vx is equal to Vx minus V out 3. Plus Vx on both sides, so we have 9V3 is equal to 10 Vx minus V out 3. Then yeah, so then well, just solve for V out 3 actually. So 9V, yeah, so actually sorry, yeah. Okay, we'll just do it this way. So 9V3 minus 10Vx, actually this would be better to solve for negative V out 3, and then V out 3 is equal to negative 9V3 plus 10Vx. I'm going to save this equation for now. Okay, so again we have V out 3, and it's a function of V3, but it is missing this Vx, so we do need to find a way to solve for Vx. Yes, so unfortunately it does look like we will have to use this bottom current path after all. I was kind of hoping we could avoid it, but we still have to just use it. Okay, so I'm just going to define it in this manner. This is KVL actually, so you can see this voltage, it goes from ground to Vx in the same way it goes from ground to Vx. So this is like a KVL KCL loop that we can make on this bottom section. So the current is in this clockwise manner. I'm going to call that I2, and recall there's no current that enters the non-inverting node of the op-amp, so there's just only this current loop of I2 going on. And so let's just do this like a KVL KCL kind of loop that go in there. You can define I2 as this voltage minus this voltage divided by this resistance, which is 0 minus Vx divided by 2 kilo ohms. In the same way that you can define I2 as if it's flowing in the clockwise loop, it is this voltage minus this voltage divided by that resistor. So it's Vx minus 0 divided by 3 kilo ohms. And we can see that the kilo ohms, it does cancels out. So we have left is Vx divided by 2 is equal to Vx divided by 3. Now you might say, oh, okay, this doesn't make sense. Well, it does make sense. You will see what happens when we do this cross multiply. You could probably see that Vx equals 0 is the only solution to this case, but let's just solve it so you'll be more clear. Let's do cross multiply across here. Yes, I know Vx is 0, but let's just do the cross multiply just to be absolutely clear. Then we can move it to the one side, so then plus 3 Vx on both sides, so it becomes 5 Vx is equal to 0. Okay, Vx equals 0. So we have here let's call the what we just solved previously, let's call this equation 1, and then we just solved now, we'll call equation 2. I will do this thing, combine 1 and 2. So V out 3 is equal to negative 9V3 plus 10 Vx, but if Vx is 0, which is negative 9V3. Okay, so we now have solved for V out 3. Let's inherit what we just equation form that we had just discussed earlier, and I'm just going to copy paste put here. So now we know that V3 coefficient is negative 9. So superposition 1, superposition 2, and superposition 3 added. Oh, V out technically is V1 plus the V out 1 plus V out 2 plus V out 3. Although V out 1 and V out 2 was solved in the previous problem, we just have to do the third superposition in this problem. And here is the final answer, it goes here.